Hello, everyone, and welcome to the second day of JAX Diffusers, kickoff event. And today we are going to host Tim, Suraj, and Sabrina. And without further ado, I would like to have Tim. Tim is working in Google Brain, and today he is going to talk about efficient image and video generation with distilled diffusion models. The floor is yours.
Thanks for the intro. Right, so for today, I will actually talk about basically 6 different papers that my collaborators and I have written over the past 2 years. So this is joint work with lots of great colleagues at Google, and I'm very grateful to them for all their amazing work. Of course, it's quite a bit of material, so I'll just give a very high-level overview. Hopefully, you'll know where to find the good bits after this talk. And of course, I can answer more detailed questions also after. Right, so to begin, I would actually like to set the stage and reflect upon what an amazing year it's really been for generative modeling. So I've been in this field for a while now, and I think the past year has really been the year of generative modeling. So at Google, we released Imagine and Imagine Video, 2 models that I was involved in. But also Fanaki is another video model that we released, and Party, a text-to-image model. And of course, outside of Google, we had DALL-E 2 and Stable Diffusion, all basically within 1 year. And we really came quite far in the years before. So when I got started in this field in 2013, 2014, we just had VAEs be invented and GANs. And well, they barely worked if you look at the samples on the left here. You can't really make out what we're generating. So then we made some advances in autoregressive models. I myself was at OpenAI at the time, and I had this opportunity to present some of my work to Elon Musk. And I actually showed him these particular samples right here. Well, needless to say, he was not very impressed. But fortunately, we made a lot of progress as a field since then. In 2019, I think we made a big step with Big GAN, where for the first time, we were really able to synthesize compelling images, still in a very limited dataset, ImageNet, where we had specific classes and corresponding images. And then again, in the past year, really, is for the first time, we're able to take basically arbitrary text descriptions of what we want to generate, and then generate truly compelling images at high resolution. So for Imagine specifically, I want to tell you a bit more about the system, the way it works and what it can do. So at a high level, it's a text-to-image model. You put in a string like sprouts in the shape of text Imagine coming out of a fairy tale book. And out comes a 1K by 1K pixel high-resolution image with quite a bit of intricate detail, as you can see here. It can do amazing things like spelling and also composition. So here we're asking for a transparent sculpture of a duck made out of glass in front of a painting of a landscape, and it actually gets all these correct and knows how to compose those into a coherent image. And it can even do this when you put in things that it probably has never seen in training, at least not in this combination, like a photo of a rainbow-colored cow floating in the space above Earth, Milky Way in the background. It can even generate objects that cannot exist in the real world, like this coffee cup. Or it can generate objects that we would not like to exist in the real world because they would be very impractical. So there's a number of things that go into Imagine and that make it possible. There's 4 main parts. There's the data. So the model itself is trained on close to 1 billion text-to-image pairs, so really quite a large scale. The model itself is based on diffusion models, of course, but we combine them into something we call a cascade. So it's a combination of different models. It also relies heavily on frozen text models, so large language models. Then there's also some advances in how we sample from this model. So we use classifier-free guidance, and we have a number of tricks to maximize the text alignment between the image we generate and the text prompt. And then, of course, we apply this at quite a large scale, which is necessary to get the best possible results. So I'll say a little bit more about these 3 aspects: cascading, the text models, and the classifier-free guidance. So at the base is the diffusion model that we all know and love. It turns pure noise into an image, but we compose it in a pipeline. So the first stage of the pipeline, we take the text prompt, we embed it into a vector space using a frozen language model, so it's not trained. We get out a set of embeddings. The first diffusion model then takes the embeddings and some input noise and turns it into a low resolution image. The second diffusion model takes the embeddings and the low resolution image and upsamples it to a higher resolution image. And we do this once more to get to our final result. And there's some tricks to make this work. For example, you need to have some augmentation whenever you train these super resolution models so that they are robust enough to actually work at test time. And we have a number of details on that in the paper. And taking it all together, this is a very effective way of generating high resolution images of the highest quality. One other very important trick that we use in this model is called guidance. So in the diffusion model, what we do is we have noisy data, which I denote by xt here, and maybe a class label or a text prompt, y. So in this case, y might be the label of dog. And then we feed this to a model that tries to denoise this to the clean image that I denote by x0 here. However, in practice, what we often do is we parameterize the model in such a way that we actually predict the noise rather than the image itself. So this can be thought of as a residual parameterization. And this noise estimate actually turns out to be proportional to the gradient of the log density of the image given the textual description or the label. OpenAI, a bunch of folks at OpenAI in 2021 then came up with this great trick to modify the prediction of the noise by adding in the gradient of a classifier model. So the classifier model takes in the noisy image, predicts dog or some other class, and then what you do is you move the noisy data in the direction of the class that you want to generate. So this ensures that you're generating something that's well aligned with the text prompt. We did some follow-up work on this using a technique that we call classifier-free guidance, where instead of an explicit classifier, we use an implicit classifier using Bayes' rule. So we say the probability of the label given the data is proportional to the probability of the data given the label divided by the unconditional probability of the data. So if we take that implicit classifier, we take the log gradient again, then we get this other term, which is the difference between the gradient with respect to x of the log density given the label and the gradient of the log density unconditional of the data of the prompt. And this difference we add into the estimate of the noise, and this works quite well. In practice, we predict noise. So when you plug in the noise prediction rather than the gradient estimates, it looks like this. So we have a noise prediction conditional on the text prompt and one unconditional. And in practice, we do that by simply training one conditional model that always takes in an embedding for the text prompt. But sometimes we set this to 0. So we just encode the 0 string. And this we take to be the unconditional prediction of the image or the noise. So this trick works quite well in ensuring that what we generate corresponds to the text. So here I'm showing you the results for a number of different settings for this W parameter in guidance. On the y-axis, I have FID. So FID is a measure of how well our model is capturing the data distribution. And on the x-axis, I have the clip score. So clip score is a measure for how well what we generate actually represents the text prompt that we asked for. So as we increase the guidance weight, we move from the bottom left of this image to the top right. So initially, both FID and clip score improve. And then as we increase guidance further, FID starts to deteriorate. So what we generate is further removed from the data distribution than for the no guidance case. But the alignment is still improving. And what we find in practice is that users often care more about the alignment than about the fidelity with which we capture the underlying data distribution. So when we combine this with some tricks where we do some clipping or thresholding to make the model stable, this results in the red line here, where we can get very high clip scores, and this corresponds to generations or images that the users find very compelling. For the text model, we investigate different classes of text encoders. We look at language models like T5 and BERT, and we also look at text encoders from image-to-text models like CLIP. And we actually find that these text-only models, they actually work very well, which is kind of surprising since they never even saw visual data during training. So we take these language models and we freeze them so we don't train their parameters, and we still find that their representation actually is very useful for generating images. And in particular, what we find is that larger text models give us representations of text that are more useful, or that the model finds easier to use in generating images. And we actually find that using the largest text models actually makes a large difference for the perceptual quality of the images that we can generate. So for us, after having done Imagine, the next step, kind of logical next step, was to ask whether we could do the same for video. And it turns out, well, we can. So we have this follow-up project called Imagine Video, where we generate short 5-second clips of video in much the same way as we do text-conditioned image synthesis in Imagine. Like Imagine for images, Imagine Video is really a pipeline of different models. So we once again start with a text prompt that we feed into a large language model, T5 XXL in this case. So that's the yellow box that you see here. After that, we take this embedding and we feed it into the first diffusion model, which is in the blue box. It's a base model that generates a very low resolution video. So in this case, just 16 frames at a resolution of 40 by 24. So for about 5 seconds, that's at 3 frames per second. After that, we then upsample this low resolution video in multiple stages. So in all the red boxes that you see in this graph, we do temporal super resolution, meaning that we increase the frame count of the video. And on all the green boxes, what we do is spatial super resolution. So there we increase the pixel count, or the resolution of the frames of the video. So we do this 6 times to arrive at our final output, which is 5 seconds of 24 frames per second video at high resolution. So I'll give you some examples of what it looks like later. The model itself at each of these stages is really quite a simple diffusion model. In a previous paper, we introduced this model that we call the video diffusion model. And it's kind of the smallest delta we can make from the image model. So basically what we're saying is that a video is kind of like an image. You just have one additional dimension in the tensor. And similarly, what we do is we take the standard 2D UNet that we used for images, and we just apply it to each of the frames in a video, and we add some additional layers that exchange information across time. So it's a standard UNet with some additional attention layers that exchange information between the frames. So here's one example of something we can generate with this. And here we ask for a bunch of autumn leaves falling on the lake to form the text Imagine Video. And quite amazingly, it can both do the spelling and it can also get the timing right. So here's another example. So what I find quite amazing about these examples is that it can both do the spelling, but it gets the timing exactly right. So the text actually starts appearing at the start of the video and completely finishes appearing at the end of the video. And this is actually not really cherry-picked. We can generate this quite consistently. Although there's nothing in the model that actually tells it that it needs to take exactly 5 seconds to generate this. There's nothing in the training data either. So really the magic that actually allows this to happen is guidance. So in guidance, we ask the model to generate something that aligns well with the text prompt within the span of time that we give it. And the only way it can do this is by actually matching up the text appearing with the duration of the video. And this is also quite unique to this way of generating, where we generate all the frames at the same time. If you would do something autoregressive, where you would generate one frame at a time, it's much more difficult to get the model to actually understand this timing without explicitly telling it that the video is 5 seconds, or that the scene needs to be completed by a certain number of frames. Yeah, here's some more examples. I can do things that are out of distribution, like a wooden figurine surfing on a surfboard in space. Another out of distribution example, a happy elephant wearing a birthday hat walking under the sea. Here's a very cinematic one, flying through an intense battle between pirate ships in a stormy ocean. And the last one, a view of a castle. So it's actually great at doing these aerial shots. There's a lot of drone footage in the data, I think. Yeah, I find this very nice also. Of course, we also evaluate our models on a number of standard benchmarks, and especially for the base video diffusion model. So here we look at UCF 101, which is a benchmark for unconditional generation of video. And there we find that we get very good results in terms of both FID and inception score. So here FID is, again, captures how accurately we represent the data distribution, and inception score is more related to alignment, similar to the clip score I showed you earlier. And on both, we do quite well. We can also do video prediction. So in video prediction, we actually get the first frame of a video or the first couple of frames. And the task is really to play out the video from that starting point. So predict where the scene is going to go, how things are going to develop. The most well-known benchmark here is this robot pushing task, where you get lots of videos of this robot arm moving around, and your task is to predict how it will interact with the objects and what will happen. So there we do quite well. Another video prediction task is kinetics. So kinetics is a collection of videos like you might encounter on YouTube of people performing various actions. And also there we do the predictions work quite well, especially if we use more fancy sampling methods like Langevin diffusion. I'll say a bit more about that later. So I've showed you what these models can do in practice, or at least if we're willing to take some time and maybe do some cherry picking and try out a number of things. But it doesn't mean that this really makes for a very compelling user experience, because naively sampling a video currently takes about 10 minutes, slightly more, for a 5-second video, which means that if you're interacting with this system, it gets boring very quickly. So I strongly believe that generative models need to be very fast in order to be practically useful. You have limited patience as a user, you want the system to be interactive, and so the systems need to be fast. Our solution to make these models faster is to distill diffusion models into models that take much fewer sampling steps. And we typically go down to 4 to 8 sampling steps without losing much quality. We developed this technique in 2 papers, progressive distillation for fast sampling of diffusion models, an iClear paper, and a more recent CVPR paper. That's on arXiv already and will be featured at the next CVPR. And what we find is that if you apply these techniques to the imaging video samples that I showed you, you can actually generate these in about 30 seconds, which I think is just about the amount of time that you're still willing to wait, and where you can still try out different prompts and interact with the system. We also have some open source code that demonstrates the basics behind these algorithms. It's all written in JAX, so it should play nicely with all the other stuff that you're building and experimenting with. So before I explain how exactly we do this distillation, I want to say a little bit more about how we actually sample from diffusion models in the first place. So here on the left, you see the standard view, which is that sampling is done by simulating a stochastic differential equation. So we get this noise from a known starting distribution, like a Gaussian, and then we simulate a stochastic process that gradually takes us into the direction of the data, which is has a much more complicated distribution. So what that looks like is we gradually turn noise into the clean image. And we do that by simulating the stochastic differential equation at the bottom here. But it turns out that actually there's an equivalent view where we have very smooth and deterministic paths from the initial random noise to the data distribution. And these paths are given by something that's called the probability flow ODE, ordinary differential equation, which is given at the bottom here. So here there's no noise term. It's a deterministic process that we can actually compute exactly if we have enough time. It turns out you can rewrite the stochastic differential equation to make it more similar to the ODE. So here I've split out in the green boxes the deterministic part, and then the remaining part is Langevin dynamics. So what this basically says is that both the stochastic way of sampling from these models and the deterministic way are basically the same thing. The only thing you get in addition when you do the stochastic sampling is some additional mixing according to the data distribution using an MCMC algorithm like Langevin dynamics. So it's this green box that we can actually hope to distill. So the green box is something you can iterate for a number of steps, and then it gives you a deterministic mapping from one point of the input noise to something along the direction to the output image. And this deterministic mapping is something that we can hope to represent with a neural net that takes fewer steps than the solver that we use to actually generate the path. So that's what we actually distill. So in order to do this efficiently, we propose an algorithm called progressive distillation, where we apply this distillation in multiple stages. And at each stage, we take a student model that is warm started from a teacher model just by making a copy. And it learns to imitate the teacher model, but it actually uses half as many sampling steps. So what that looks like is something like this. On the left here, you see a teacher model that takes 4 steps. And what we do is each of these for 2 steps, we try and distill that into a student model that does the same thing, but with only 1 step. So the first 2 steps get distilled into something that takes 1 step to get to the same point. The second 2 steps get distilled into something that also takes 1 step. And now at the next stage, we take this new student model and we turn it into the teacher model, and we repeat this process, where we now go from 2 steps into 1 step. So you can imagine if you start out this way with many steps, you can iteratively halve the number of steps required. And this works quite well in practice and is very computationally efficient. So looking at the algorithm, it looks like this. So on the left is the standard diffusion training code, and on the right is progressive distillation. And the main changes are highlighted in green. So I'll go through them step by step. So in progressive distillation, we start out with a trained teacher model. So the way I've written it here is it's a prediction of the clean data, X, with it using as input the noisy data as ZT. At each iteration of progressive distillation, we do a warm start. So we set the students equal to the teacher by copying the parameters. And then comes the interesting part. So the interesting part is where we set the target that we train the model against. And we determine that target by running 2 steps of the DDIM integrator. So DDIM is one way of integrating this ODE that I showed you in the past slides. And it's the most efficient integrator that we have. So we use 2 steps of DDIM to get you a next step in the sampling chain. Then from that next step in the sampling process, we back out the targets that our student model we need to predict in order to get to the same point in 1 step. So that's given by this formula. And then this target is what we actually plug into the loss for the model. So this is what we ask the student model to predict. So we do this for a number of steps until we're happy with the results. And then the student becomes the teacher for the next iteration of this algorithm, and we halve the number of sampling steps. So what we find is that this works quite well on standard data sets. What I'm showing you here is the FID for a distilled model for a varying number of sampling steps. And I'm comparing it to DDIM and to a stochastic baseline sampler that is separately optimized for each number of sampling steps. So it's quite a tough baseline to beat. And we find that as you decrease the number of sampling steps by a lot, and the distilled model does much better. And in particular, we find that 4 to 8 sampling steps is kind of the sweet spot where you don't lose much in terms of quality, but you do have a very large speed up compared to naively taking as many as 5 to 12 steps in this case. So that was the first paper where we showed this as a proof of concept on ImageNet and on other data sets. In this more recent CVPR paper, we extend this in multiple ways. So we showed that this approach also works with classifier-free guidance. We show that you can actually use the distilled model to do stochastic sampling, not just deterministic sampling. We show that it works for text-to-image models, not just class conditional generation. We do image-to-image translation, we do in-painting, and we show that this actually also works for latent diffusion models. So most of the samples that you see in this slide are actually generated using a distilled model of distilled version of Stable Diffusion. I'll tell you a little bit more about some of these aspects. So in particular, the way we actually distill models with classifier-free guidance is in 2 steps. In the first step, we take this classifier-free guidance model that actually takes 2 passes in order to take 1 step in the sampling algorithm, and we distill that into a model that only takes a single pass. We do that by sampling a guidance coefficient, so that's the W parameter I showed you earlier. We sample this from a particular range, like between 0 and 4. Then we find the teacher prediction that corresponds to that. So we did 2 passes through the teacher model. We apply the guidance formula and we get a prediction out. And then we try and match that with a student model. And the student model takes as input also the guidance weight W. So in addition to the input data and embedding of the time step, it also takes an embedding of the W parameter. So you train that for some time, after which you have a single model that now does in a single step what the old model did in 2 passes. And after that, you can just do the progressive distillation that I previously explained until you're at the number of steps that you're happy with. Now we have a deterministic model that takes many steps. And previously, we only did deterministic sampling using that approach. So that corresponds to the top of this slide, where in this case, we take 4 deterministic steps, shown by the blue line, to get to the image that we give as output. But it actually turns out that we can also do stochastic sampling with this. The way that works is that we just simply double the step size that we use for all the deterministic steps. So the blue steps are twice as big. But then after each deterministic step forwards, we actually take a step backward by adding noise back into the image. So adding noise back into the image is just exactly the same as what we do during training. You take in a clean image or a halfway clean image, you add a little bit of noise in. And because we can actually split out this STE into a deterministic part and a noisy part, you can actually show that this is actually also a very accurate way of sampling from this process. And what we find that this is particularly useful for cases where we use high guidance weight. Lots of numbers here. I'll show you 2 in this red box here. So in this red box on the left, you see the number for the deterministic sampler, the inception score that you achieve with the deterministic sampler using 8 sampling steps and a guidance weight of 4. And the right number in the red box is the same number you get by doing stochastic sampling. We find this is generally a bit higher when using few steps and high guidance weight. So this and this also translates to images that we find a bit more compelling. Finally, what we find is that this algorithm is directly applicable to latent diffusion models like Stable Diffusion. Chelin, the first author of the paper, applied this to Stable Diffusion, where you can get quite good results using as few as 2 sampling steps. So to summarize the talk so far, I think generative models are really no longer just a science project. When I got started in this field, they clearly were. No one is going to use the samples on the left here, But now we're at the point where these models actually produce quite amazing things. And I'm confident they will end up in lots of products in the coming years and will be very impactful. Diffusion is becoming quickly the new paradigm for achieving state-of-the-art results using generative models. It's a very flexible framework. It's stable. It's not like a GAN where we don't really have a proven convergence. That's more of an empirical science. But really, we have a simple loss term that we can minimize and use to train our model. And finally, I believe strongly that these models need to be fast if we actually are going to use them. And our approach to that has been distillation, and that's been proven very effective so far. All right, thanks. I can now take some questions.
Thanks a lot for this talk. This was my first time seeing distillation outside of transformers, honestly. I really like the idea and the intuition behind it. And we have a bunch of questions. So Patrick is asking, I'm not sure how much Tim can talk about this, but I'm very curious if Imagen would have similar performance if it would have been trained only on public data.
Right, so data is, of course, very important. There's a lot of data out there on the internet. I'm sure you could get similar performance training just on public data, but then the question is, how do you curate the data? So just taking every random JPEG you can find on the internet, that won't work. You will need to put some time into actually selecting the right ones. And if you do, I'm sure it can work. And at Google, we're definitely exploring lots of different data sets and finding that different data sets are appropriate for different purposes. But that, good results can be achieved in a variety of ways.
And the second question is, can we do the same with all types of noise or distortions, not just Gaussian? Also, is the noise required to be uniform over the entire image, or can we have areas with more noise than others?
Right. That's a good question. So there are some works in the literature where they use different types of noise. But in general, all of our results do depend on this infinite divisibility of the noise. So one thing that's very unique about a Gaussian is that if you add two Gaussians together, you still get a Gaussian out. Or put it the other way around, if I give you the noisy data, you can actually decompose this into a number of additive noise terms that are actually consistent with the output distribution. So there's ways of doing something similar with different distributions, but it's quite tricky to get something that's theoretically justified. So I would say in general, yes, it needs to be Gaussian. What we do find is that you can actually add more noise in certain directions than in others. And we actually have a paper called blurring diffusion models where we do a transformation of the image, where effectively we're adding noise in particular directions more than in others. And this also works quite well.
Yeah, Emil talked about it a little yesterday because people were asking about it. And our third question is from Patrick. People are playing around with using character-based text encoders now, such as BT5 or K9, hoping that they are better at generating exotic text. What do you think about this?
Right. So what we do find is that if you wanted to be able to do spelling, like in this last example that I'm showing you, then of course you do need to actually represent the individual letters in your embedding. So big text models like T5 already do that quite well, but I imagine that doing character-based encoding actually is even better if that's what you care about. There might be a trade-off though between capturing the feel of an image and exactly representing a prompt. So something like a clip-based encoding, like in DALL-E 2 and also in some other things that we tried, that is actually quite effective for capturing the general feel of a prompt. So in the DALL-E 2 paper, there's some very nice examples of that, where they take a logo, they encode it, and they generate multiple logos that kind of look the same. And that's something that I'm not quite sure you would get from an embedding from a text model that has never seen visual data.
And another question is, this sequential approach with many large blocks seemed quite expensive. Do you notice much poorer inference times for video Imogen?
So as I mentioned, for Imagine, for video Imagine, for the base model, where we take 7 different steps, 7 different diffusion models, and we use 256 to 128 steps to sample from them. It does take over 10 minutes to generate a short 5-second video, so that is indeed quite slow. So there's different ways of speeding that up. One approach is the distillation that I talked about here. Another is the one that Emil talked about yesterday, where rather than having this sequence of multi-resolution models, we actually try and generate at the highest resolution from the start. We can actually do that quite well now, mainly by making some changes to the noise schedule that we use for sampling. And this is definitely something that we're still working on, and I think these models will get faster and more efficient as we make progress there.
Another question is, at what video length, assuming the memory allows for it, do the videos become inconsistent?
Right. That's a good question. So in the video diffusion models paper, we also present a way of autoregressively extending this video. So there's advantages to generating the whole video in one go, which is what we do in Imagine Video. But then if later on, after training for 5-second videos, you decide you actually want them to be extended, you can actually do that using these models. So just as a proof of concept, we actually tried doing this and generating like minutes-long video for a particular text prompt, and it does actually work quite well. We don't really ever diverge. It's just the alignment between the text prompt and the video can deteriorate a little bit. So, for example, if you're generating a person lifting an item from the table, then the first 5 seconds with high guidance, that's exactly what happens. Then if you extend that video, you see like a person with an object in their hands, like standing around a little bit, and it's not that interesting. So you don't gain that much from it. But it's certainly possible, and it doesn't diverge, and that's quite a nice property of these models.
And we can have maybe 2 more questions. Let's see. I think this is a good question. Do you imagine that progressive distillation could be adapted to distillation of models in other fields?
Right. Yeah, so that's a very general open question. So these diffusion models do have a very specific structure where they take many steps to generate something that we actually know deterministically. And that allows you to then amortize taking all the small steps into something that takes one large step. So amortization is something that is used extensively in machine learning. So for example, in AlphaGo, you might take many steps to arrive at a particular move on a Go board or on a chessboard or something similar. And then you can train your neural net to guess that move from the start without going through this whole search process. So I think intuitively, that's actually very similar to what we're doing here. And I'm sure that basic concept is applied to many different applications in machine learning and in other fields. And yeah, hopefully progressive distillation can be an inspiration for trying even more applications.
I would imagine for stuff like AlphaGo, it would be quite expensive to get somewhere, though. But this is just a comment.
Yeah, I mean, that is true, right? Like in AlphaGo, almost all the computers in search, or in every search step you evaluate in the neural net, and if you search very deeply, then the base model or the first time you evaluate the model, that's only a very small part of the compute. But then what they find in their case is that if you train this well enough, then even the first step is pretty decent. And this is similar to how our distilled model is still very slightly worse than the base model, but it gets you most of the way.
So let me see if there is like a cool question. There is like a lot of cool questions, but I'm trying to pick the best one because we will host Suraj soon. You say that diffusion become the dominant paradigm, and I agree. Do you think the recent consistency models could become the new paradigm, 1-2 step without distilling?
Right. So the recent consistency models paper I quite liked. Like mentally, I still place this into the diffusion paradigm. It's very closely related. And I actually think that their strongest results were also still distilling from a trained diffusion model. So their paradigm does allow for training from scratch, but the best results that they achieved were still using distillation.
And Boris is asking, is a pipeline of multiple models necessary, or could you use a large model end-to-end?
So using a large model end-to-end is something that we have explored and that Emil talked about yesterday. So I'm sure you can still see that talk also. It is a bit more tricky to train that correctly, but we're making a lot of progress there. Yeah, once again, you need to adjust the noise distribution and maybe also adjust the model. But I believe we can indeed train one big model.
And this was the last question. I really liked your presentation. Thank you so much for accepting to speak today.
Thanks for the opportunity.
Thank you. See ya.
Bye.
And now I will be hosting Suraj from Hugging Face, and he will be talking about mask generative models, which was something that I was very curious about. Would you like to share your screen?
Yes, yeah, okay, can you see it?
Yes.
Let's go.
Okay, I will leave you with your presentation. Good luck.
Thanks, Nave. Right, hi everyone. I'm Suraj. I'm a machine learning engineer at Hugging Face, and I mostly do open source stuff. I was a co-maintainer of transformers, and then now I'm a co-maintainer of diffusers, and I'm mostly working on open source text to image models. So today I'm going to talk about this new method for image generation using discrete tokens, which is which was recently proposed by Google, and it's called mask generative models. So basically, it's a transformer-based mask language model that can do really good image generation. And the papers like MaskGit and Muse have established state-of-the-art results on some image generation tasks at the time of publication. So this talk, I mean, I'll briefly talk about why do we need these models and what are the limitations of current models, and then I'll briefly present what Muse is, and then we'll go deep into how these models are trained and how to do inference with these models. So I mean, as like everyone knows that the most dominant approach for image generation right now is diffusion models. We really don't need any introduction for it. And another really popular approach before diffusion was autoregressive transformer models, like the first Dolly model, and then Dolly Mini and Parthi, which uses like a two-stage approach where there's a VQ-GAN which can take an image and create a discrete representation of it, and then we use a transformer model, an encoder-decoder transformer model that can autoregressively generate the image tokens by doing cross-attention over the text. And especially Parthi has like really great results on these models. But one of the limitations of both of these approaches is that these models are slow at sampling time. Okay. One side note here that the diffusion field is very fast moving, and then we have some new methods like consistency models and distillation, which can bring down the sampling time by a lot. But right now, I say, for example, if we take stable diffusion, we need to do like at least 20 or 25 steps to get good generations. If you have an autoregressive model like Dolly Mini or Parthi, and if you're generating 256 tokens, then the model, you need to run the decoder for 256 forward passes. So it's like the inference cost increases by a lot. And especially if you want to do high resolution generation or video generation, then that becomes a bottleneck. So instead, these mask models like Maskit and Muse offer like a more efficient approach compared to these other methods. They use a bidirectional transformers, and these models, because of the way they are trained, they are able to predict multiple tokens simultaneously, predict multiple tokens in a single step, and that way, like they can accelerate the decoding. So instead of having to do like 256 steps, you can do like 4 steps, 8 steps, or 16 steps, depending on the kind of quality you want from the image. So that's kind of a more motivation for these models. So now we'll go over like how MaskGit actually works. So MaskGit stands for like Mask Generative Image Transformer, and like the first dolly and the party model, it's a two-stage model. So the first stage is a VQ model. I won't go into the details of VQ models here. I think you can look into taming transformers, or there are lots of cool resources for understanding VQ models. But basically what it does is like the VQ part also has an encoder and decoder. The encoder takes an image and then creates a discrete representation of it. So like you get like discrete integer tokens, and the decoder can take those discrete tokens and turn them back into the image. And then there's another transformer model, which is a BERT like mask transformer model. And the way we train this model is we get these discrete representations, and then we mask a bunch of tokens in the from the input. For example, here the gray tokens are mask tokens, and then we feed it into the transformer, and then the transformer is trained to predict these mask tokens. So it's like a two-stage approach. There's the VQ stage and there's the decoder stage. But the decoder is not autoregressive. It's a masked language model, but it's a masked model. It's not a language. So during training, Maskit learns to predict randomly masked tokens by attending two tokens in all directions. Like this is one of the key thing here. For example, images kind of have bidirectional tokens. It's not like language where the future tokens only depend on the past tokens, and the past tokens are not influenced by future token. But like in images, like you have bidirectional dependencies. So what mask git does is like instead of using a causal mask, it uses, since it's a mask model, it uses a bidirectional mask. So each token can attend to every other token. So it in a way it has more context. And then at inference time, we start with all mask tokens, and then the model keeps on predicting the mask tokens, and then we keep on iteratively improving the generation. So that's kind of the basic overview of Maskit. Now, during training, what we do is, as I said, it's a two-stage model. We use a VQ model encoder to get a discrete representation of token, and then we sample a subset of tokens and replace them with a mask token. This is the key part here. For example, if you are doing mask language modeling in NLP for such as BERT, you use like a fixed masking rate of 15%, and you mask like 15% of any random tokens. But in MaskGit or in Muse, what we do is we use a scheduling function, and that scheduling function tells us how many tokens to mask. So the masking we do here is a variable. We don't have a fixed masking rate of 15%, because this is to be able to to emulate the inference scenario. We use a variable masking rate, so the model can see like what to do when all tokens are masked, what to do when like some partial tokens are masked, and which is a really key thing to get this model to work, to use a variable masking rate. And then the model is trained to predict these mask tokens by attending to all the tokens. And this, like, apart from the scheduling function, the maskit training is exactly similar to how you would train a BERT model. So but instead of the language tokens, you have the discrete tokens of image given by the VQGAN. You use a variable masking schedule. For example, for one example you would mask 40%, another example you would mask all of the tokens. For some examples you would mask like just 5%, 10%, or 1% of the tokens, and then the model is trained to predict these mask tokens. And then during decoding, as you can see in the image, what we do is we kind of fix the number of steps. For example, we say like we're going to do the inference in 7-8 steps or 16 steps. And then when we are starting the generation at T0, we start with all mask tokens, then feed that input into the model, and then then the model predicts those mask tokens, and then we choose some tokens which have like a bit of a higher probability. For example, you check this, like the dark gray area here is the token selected at that time step, and then we keep on iteratively doing this. Like at each iteration, we select some tokens which have a high probability, and then we mask out the remaining tokens and keep on doing this generation. So at the last steps, when we are here, we then, once we have like a lot more tokens generated, we just at the last step we predict like all the remaining tokens, and then we have a final image. Also, the key thing you notice here is that when we start the generation, the number of predicted tokens are very less. For example, in the first step, there's just one token, then we have like 7 or 8 tokens. But as we get more context, we choose like multiple tokens, which sample multiple tokens. That's because the model has more bidirectional context. And to introduce the diversity in generation, we use temperature annealing. So like instead of choosing the token with the highest probability, we set a certain threshold, and depending on the like from that threshold, we just randomly sample some tokens, and this helps the model to like retain diversity in the generation. And yeah, so that's pretty much how training and generation with maskgit works. And another cool thing apart from these models being fast is that these models, due to their nature of training, support a lot of image editing tasks out of the box. For example, they can do zero-shot inpainting or outpainting, they can do image extrapolation and zero-shot mask-free editing. Like, because the model is trained to predict mask tokens, you can, to do inpainting, you can just like only mask out the tokens in the masked region of the image, and then ask the model to predict those, and it works pretty good, as you can see in these examples. Again, the key thing here is that these models are not trained to do inpainting, outpainting, or like mask pre-editing. It's just due to the nature of training of these models, they can like they have the zero shot ability to do inpainting, outpainting, and mask pre-editing. And the next step of maskgit is Muse, which is basically like a maskgit model, but it's for text to image conditioning. So it has a text encoder as a conditioning, and then the model takes like as maskgit, it takes the mask tokens, but also does cross attention over the text embeddings to generate the image. And Muse is a two-stage model. So the first stage generates a 256 by 256 image, and then in the second stage, it's also very similar to the first stage, but it has two contexts. It takes the generated low resolution generated tokens from the first stage and also the text embeddings, and then does cross attention over both of them, and then generates a high resolution image. And one of the reasons we don't directly generate 512 by 512 image is because sometimes the model can generate high frequency details. So instead we choose the two-stage approach. And the results with Muse model are really great. These are some of the text to image samples. This is some of the zero shot mask inpainting. And this is mask free editing. Like you just provide an image and you just mask a bunch of tokens from that image and then just give any prompt, and the model has the zero shot ability to edit it according to the prompt without using a mask. Yeah. And yeah, so it's all great, but it's not, as with like other Google's text to image models, it's not open source, which is kind of not a good news, because it's when the models are not open source, like the community can't try out the models. It's very hard to evaluate the models. It's very hard to understand the capabilities of the model. And for example, evaluating models is notoriously hard. Like the current metrics like FID or clip score don't completely capture the capabilities of model. But instead, like if we give the model out to the community to try it out and like do different kinds of generation, use different types of parameters and whatnot, we can like very easily assess the qualities of the model, find out different biases. One of the great examples is Stable Diffusion. I mean, like everyone has seen the explosion of Stable Diffusion, and most of the like the things that we can do, the community has done with Stable Diffusion. Also, most of these now the current like a lot of methods like tune a video or control net are now based on Stable Diffusion. So it's because like that single model was open sourced, a lot of new methods and applications came out of it. And so in the spirit of open reproduction at Hugging Face, we have kickstarted a project to openly reproduce Muse, and we are collaborating with Robin Rombach, the creator of Stable Diffusion, and the open source community to openly reproduce and train Muse model, and then along the way share all artifacts, code, and learnings with the community, so the community can build on top of it. We have open sourced the code at this GitHub URL, and all the intermediate checkpoints will be available on the hub as we train them. So far, we have two models, just class conditional models to test the approach, and so far it's been going well. And the plan for the next couple months is to scale up the model and train it on bigger data sets. So stay tuned, and if you have any feedback, just go to the repo and share your suggestions, or if you want to interact, or if you want to join the efforts, just feel free to just comment there. It's going to be all open source. Yeah, that's it for me.
Hello. I really like the idea. It's very often that when you are like when you are training masked models in text, like you only can learn about the distribution of things, but like you cannot really do the stuff like I don't know how it would work for text, but like in painting and out painting with masking is like very intuitive, and I really liked it.
Yeah.
I had this question, but it was like a bit of a stupid question because like apparently when you do masking, it's like it's like masking in the like when you are masking patches and other stuff. It's not like you don't have bidirectionality, but you have non-directionality actually, I think.
It's a I'm sorry, I didn't get the question. Could you
So like
ask it
you
again?
directly feed the so basically you mask the tokens and then you directly feed the thing itself, like the mask the image itself, right? And
Yeah, yeah.
that was why I was saying it's not really bidirectional, it's like non-directional actually, like you don't really try to predict the next thing or like yeah, it's a bit like BERT.
Yeah, exactly.
So we have like a couple of questions. It's Alex is asking, once a token is unmasked, can it be changed again? Say mask token, arrow of token X, arrow of token Y. I don't know.
I think ideally it can, but the way we train these models is just like once a token is predicted, there's we don't have a surety that the model will like predict another token for that position. It's also one of the question I want to like do a bit of research on as part of Open Muse. Like for example, during training, instead of just replacing a token with mask, can we replace it with some random token? So the during inference we can like repredict the like mask the unmasked tokens again and then repredict those.
And another question is it possible to use other sampling techniques than temperature-based analogous to sampling from language models, top K, top P, or locally typical sampling?
Yeah, it's definitely possible to use any of top K or top P. This is the sampling is very similar to the way we do it in NLP.
Cool.
For now, we are just using temperature based because that's what was proposed in the paper, and we wanted to kind of train the models and compare it with the paper. So we kept
Is
the
it
temperature-based code.
like, did you try to like infer, or are you still training? Is it hard to get right, the search parameters and like the temperature, top K and more?
It's like the default parameters sometimes work, but to get best generations, I think you just need to kind of do a hyperparameter search, like just choose a bunch of values for temperature, top K, top P, and then just evaluate the models.
Cool. Another question is, does the future steps can impact already unmasked tokens, or was it trained in a way that only unmasked tokens can impact future tokens and not the opposite path?
That's an interesting question. In a way, like there's no future step here because the model is bidirectional.
Yeah.
And kind of it does attention over all the tokens. So both masked tokens can influence unmasked tokens, and unmasked tokens influence masked tokens.
Yeah, that's what I guessed as well. So Christopher is asking, can sometimes explain to me, like I'm 5, how tokenization works for an image?
That would be a different talk in itself, but I'll try to see if I can find some slides. So the tokenization, I think we use vector quantized VAE or vector quantized GAN here. It's basically like a VAE, but there's a discretization bottleneck. So the basic idea is like what you have an encoder, and then you get some sort of embeddings. There's an embedding table, and then the discrete tokens are the tokens which are kind of represent those embeddings, and the model is trained in such a way that like as the model compresses the image, it's able to find the nearest embeddings using the tokens. I'm not sure if that makes sense. I don't have the slides or like any diagrams for WikiGAN now, but I'm happy to explain it on the repo if you ask the question there.
Andreas is asking, how different can the unmasking during inference be from unmasking during training?
How different?
Like,
I think.
yeah, go on.
Go ahead.
No, I just wanted to explain the question.
Yeah, I didn't get the question completely. So.
I think Andreas clarified it a little bit. How different can the unmasking strategy during inference be from the unmasking strategy during the training? How does this impact quality of the generated image?
I haven't really experimented with it, and there are no details in the papers as well. So it's I guess we'll have to find out.
Cool. And this was the last question. Thank you so much. I really liked your presentation.
Thank you, Marve. Thank you for
See
organizing.
you.
See you.
And I can have Sabrina now. Hello, Sabrina.
Hey, how's it going?
Good, good. How are you?
Doing all right. Just came from a wild kayaking trip that had to be aborted thanks to weather conditions. So we got to ride on a fast boat with park rangers and law enforcement. Delightful. But yeah, so that's why I'm in this Airbnb with just my laptop. So no funky two-screen magic.
Thanks a lot for making time to present today.
Yeah, for sure.
Would you like to share a screen?
All right, let me do that. Window. There we go. Do you see the slides?
Yep, perfect.
Wonderful.
I will leave you with your presentation then. Good luck.
Alrighty, thanks. Hey, so I'm Sabrina Mielke. I'm a grad student at Hopkins, hopefully finishing soon. I've kind of spent my time writing my thesis lately, which is why I haven't been doing that much new stuff with JAX. And if you look at this little tagline here, it says the slides are almost 2 years old at this point, and the blog post that it's all based on is even older, but we're going to get to that in a second. So the talk title is kind of a mouthful, from stateful code to purified JAX, how to build your own neural net framework. And I guess it's somewhat of a different talk than the ones that you've seen before, in that I'm not really going to be describing interesting results, new models, state-of-the-art, bleeding-edge things. I really want to give you more of an insight and a bit of like a hand-holding to your own tinkering with some of the frameworks that you're using in this workshop and other stuff you might see in the JAX ecosystem. So when JAX first really became a thing, a topic people were interested in, it was often described as like NumPy plus something. So you might say it's NumPy plus JIT. So an implementation that used to be on CPU, like in this paper some students and I wrote back in the day, you could have like an sklearn implementation that was great, 10 seconds on CPU. But you're like, well, we're in the age of GPUs. Can't we put this on the GPU? And with JAX, well, that's super easy. You just implement it, call JIT on it, and run it on your accelerator, and you get some nice speed ups that way. In fact, when I started messing around with it, I had this little thing where I was like, okay, how fast can I make LSTMs go? Because they weren't like entirely dead at that point just yet. And Jeff Dean actually retweeted me, and I'm so happy. It's just the highlight of my career. So you can have a lot of fun just by making things fast with JAX. Okay, fine. But then interesting for us is also, of course, the gradient taking, right? If we want to do something with gradients, which we do, that's kind of all we do in a way. It makes sense of JAX to think of JAX as NumPy plus gradient taking. And this is not just your boring old gradients. You can do pretty wild things like super easily. I don't know how many of you are familiar with reversible jump MCMC. If you're doing like Bayesian sampling, you might have run into MCMC, and reversible jump is kind of a cool way to change dimensionalities. But anyway, I don't really want to talk about that, and you don't really need to look at all of this code. What I just want to highlight is that the math says you need the Jacobian determinant of a diffeomorphism. And okay, you look that up, you implement your little diffeomorphism, that's just a function like this. Okay, it's literally just a Python function. How do I get the Jacobian determinant of that? Well, with JAX, I literally just call the Jacobian, get this reverse mode Jacobian, then I get the determinant, and voila, that's all I need. Pretty wild, like super convenient. Imagine having to do the math. Nobody wants to do that, right? So that's cool. And then, yeah, you add your JIT on top of the grad, and you VMap it or PMap it, and speed, amazing. You can do some very fun things with that. But what I want to talk about here is more like if you're coming from the previous age of frameworks, so think PyTorch and eager mode TensorFlow, once you look under the hood of how these things work, it gets kind of weird. You're like, where's the dot backward, and how is this actually done? And so how do we actually implement a neural net framework, or even just train a neural net with this sort of technology? To show the difference, here's kind of what you would imagine it would look like in, say, PyTorch. If I take two tensors, let's say W and X, and I multiply them to create a new tensor Y, what this tensor Y is actually going to have is not just the storage for the data, not just the number, 546, but it's also keeping track of where it came from. It's keeping track that it was the result of this particular memory object that is the tensor called W, and this particular memory object that's the tensor called X. Oops, there goes the chat. Oh well. So this is kind of nice because now every tensor knows where it's coming from, and so if you want to do a backward pass, well, every tensor just goes to its predecessors and so on, right? This is what we can see here. Once we are calling dot backward, starting from usually the last node, but just the final node of your graph, we reverse mode autodiff by following these connections and thus propagate the gradients at the top all the way down to the leaves, where usually we're interested in the gradients of the weights. Okay? So that's how it works in PyTorch. You build up your graph just by writing out the math. You call dot backward, and whoops, everything has gradients. Wonderful. In JAX, it's a little different because everything is pure, and we're thinking a lot about transformations. What do I mean by that? First of all, what we're writing are pure functions like this. I've called this function f, very creative, I know. And it does the same thing we've done before. We just multiply these two tensors, w and x, together. You can draw a little picture. Okay, it's like two things go in, one comes out. Wonderful. And now if I want to get the gradients in there, what I do is I transform this function. I take just the function f, no values, call JAX grad on it, and it gives me a new function. I've called dftw. It still takes the same inputs. It still takes the w and the x, but now it gives me the gradient of what used to be the singular return value of f, with respect to w and x, or by default, just with respect to w, the first parameter of a function. That's why I've drawn it this way. Okay, so great. Now that looks like what I remember from high school in math. You do derivatives. That's, yeah, you get a function. Now what? How do I work with this, right? Well, I evaluate this function using my current w and my current x. I mean, imagine w being weights and x being the data. And I get the actual gradient value, which is in this case 42, the gradient with respect to w. And that's the same as it was here in the PyTorch case. That also gave me everything else. Okay. So that's how I do it. I transform the function. I evaluate the transformed function. I get a number. That's my gradient. Or I get a tensor. That's my gradient. Okay. Great. That's some nice toy examples. But how are we actually going to go from these three-liners to training a big neural network where it's not just a function f that multiplies its two inputs, right? Or said differently, how can weights and gradients be stateful if our tensors can't be mutated? For those who are terminally internet brain at a formative years in their life. So as I said, this talk is based on this blog post that I wrote in March. Yeah, that's right. March 2020. It's like multiple lifetimes ago, wasn't it? And so you might feel like, wow, that's great. That's really exciting. We're getting like the reheated leftovers. You might ask, is it still relevant? And the answer is no. It never was relevant in the sense that it never really dealt with like, oh, state-of-the-art things. This is idiomatic code. This is cool results. It's really like a post you could have written a long time ago, just about the theory of it, but something that people are now interested in because all these big frameworks are out there and we want to maybe contribute to them or just understand what they're doing. And I found it really hard to understand what they were doing when I started out with JAX. So that's kind of where this is coming from. Hope after this talk, it'll all make a lot more sense to you and you're not going to have to trial and error your way through it like I did. So what are we going to accomplish? Again, there will be no shiny, funny things to look at, no eye candy. There's not going to be any idiomatic elegance. I will not claim that my coding style is the right one. It just kind of works and small enough that there shouldn't be too much wrong with it. And we're also not going to do many of these cool things that I was talking about earlier. We're like, yeah, you can batch, distribute, and compile, because it's kind of orthogonal to what we're trying to achieve, and you could always add it on top. What we are going to do, though, and finally I'm saying something positive, we are going to be looking at the dead simple example of linear regression, good old mx plus b. We're going to do it statefully, so like the PyTorch way, try and train it on some data, and, okay, just a reminder how we used to think this stuff worked. Then we're going to be trying to move this example to JAX while dealing with this notion of purity that is required for gradient taking there. We're going to have a little aside. You can get a coffee if you're not that interested, where we're kind of like, what if actually we could do this cool thing that people don't do, but you could do. And then we're going to be working towards the actual foundations of a framework that kind of does the work that we did in step 2 for us. And finally, we're going to find out, that's what these frameworks do all along. Big surprise. Sorry, I spoiled it. So here's what a module looked like in PyTorch. I don't know how many people still remember. I feel like I've half forgotten. I literally had to like watch a recording of this talk yesterday and last night, being like, oh yeah, that's the stuff. That's right. But what you see is essentially that modules own their weights. There are these parameters, which are just wrapped tensor objects, and they're assigned to this unit, this LSTM cell. And then in the forward method, you use them when you build this execution graph, this tape that we've seen before. So far, so good. Once you do like your actual training loop, what you're going to be doing is create your instance, instantiate all the weights, and then call dot forward, which uses the current weights, dot backward, which starts this whole process of going backwards through the graph, right, and writing out all the gradients everywhere. And then once we have gradients on all our leaf nodes, apply them to the data, like if this was in the SGD. And that's basically how you would do it in like the most bare bones way with PyTorch. You mutate the gradients by calling loss.backward, and you mutate the weights by calling param.data minus equals. Right? And both of these things are no longer allowed once we move to JAX. Now, I'm going to switch to the notebook part, and I hope you can still see this, and I hope my runtime hasn't died. Oh no, but this runtime has died. Well, that's no good.
Everything seems to be fine except for the runtime.
Okay, wonderful, wonderful. All right.
By the way, I wanted to just comment that I wish they actually would teach deep learning frameworks like this in schools. Like, I've been enjoying your talk a lot.
Thank you. Thank you. Damn, it has the wrong font. I tried to get it to go comic code ligatures again. This is one of my favorite coding fonts, but I guess it only lasted one cell. Depressing. What are we gonna do?
Some people are asking if you could make the font bigger.
Oh, right. Let me do that.
Yep.
How's that?
Thank you. Yeah, it looks good. Thank you.
All right, so this is the thing that I just said. We're doing linear regression. We're doing it in Torch. We're being very boring. We have our weights. They're being owned, blah, blah, blah. Prediction uses self dot something. We have a loss function, in this case, just root mean squared error, that, again, uses the parameters that are owned by the module, blah, blah, blah. Number comes out. Let's create this object. And then let's test it out for a second. Does it predict for the number 3? Well, it predicts 0, which makes sense. We've initialized the things to 0, right? 0 times 0 plus 0. 0 times 3 plus 0 is 0. Wonderful. How exciting. Let's do some training, though. We're going to create a very small data set, literally just one example, that 3 should be mapped to 7. And since we already know that 3 is mapped to 0, what do we expect the root mean squared error to be? About that. It should be 7. So far, so good. So now that we have a loss that works, we can do a little bit of training. So let's make the data set a little bigger so we're not like totally underdefined. You can make out in your head what M and B fit this one, but it should be fairly straightforward. Let's just train this. We get the loss, we backward. We go through the parameters, we add the gradient, blah, blah, blah. We do this little step that when I learned this stuff, I always love to forget and wonder why my networks didn't train properly. And then hopefully we're going to see this prediction come closer to the true answer, which is 7. And let's see. Voila, yes, wonderful. It goes there. It doesn't really hit 7. Our step size is too large. We should be smart with it, but we don't want to be smart. We just want to be smart enough. For this talk, that's going to be enough. Okay, so that's the PyTorch example, just to refresh your memory. You can come back from your coffee break now because we're going to be looking at it in JAX. This is how you might try to implement this thing in JAX. You're like, okay, I'm going to make a class. I'm going to make weights and stuff. They're going to be owned by the module. We predict, and then we do the RMSE. Yup, cool, very similar. Nothing interesting happening here. Let's see what happens on this one. We should predict 0. Yup, and we should have a loss of 7. Yup. So far, so good. It's a very direct translation. But now we're going to start running into issues because now we need to get gradients, right? What do we take the gradient of? Well, we usually take the gradient of the loss function, right? The loss function is RMSE. And things get a little weird here because this function is not at all pure, or at least it doesn't make sense to think of it as a pure function because it takes the entire object, and differentiating with respect to a Python object seems a little weird. So before I go even further into this discussion of purity, that just sounds very strange, and we're not on the same page what it means, let's go look at some examples. I've written down 3 functions here and already given away the answers. The first one is pure, the second one impure, and the third one pure again. And I want to illustrate some things on these functions. Basically, a pure function, the idea is something goes in, something goes out. That's all the function does. It doesn't mess with any of the other stuff that's around in the ambient atmosphere. So for the first function, that certainly is true. We put a number in, and twice the number comes out. Nothing has been mutated or illegally accessed. Mutation is why the second function is no longer pure, because if I call it, it is going to actually change the list that I'm giving as an argument. So to illustrate this, let me define a list down here, L, and call impure function 1 on L. Out, and let me do it again. The list has changed. In fact, it has changed, oops, not XS, L. In fact, we can see very clearly that L is no longer the same. So this function is like evil. It took something, and then it didn't do stuff with it and got something else out. No, it took the list that I gave it and messed with it. That's a no-no. It's also kind of easily spottable by the fact that you called this function twice with what was supposed to be the same input, and you got different results. It's a lot of sketchy stuff. Right? On the other hand, this function over here, this pure function, also gets a list and also does some list magic, but it only appends internal state. So it defines this new variable ys, and that variable, you can append stuff, that's fine. You can return the variable for all you care, as long as you don't mess with your arguments and don't mess with anything that's outside of the function, everything is fine. And we can see that that's true. Like calling the function multiple times gives me the same result, and the original list is still the same it was. That looks pretty pure to me. So that's nice. Let's do some more examples. Here's some more impure functions that are a little more interesting to look at. And while you look at these functions, I'm going to look at the chat since my phone fell down. Okay, cool. Yeah, what's wrong with these functions? Well, for one, I've already talked about this ambient state nonsense, and this impure function too very obviously mutates global state, right? Does this, it drags the number executions variable from the global state into the function, changes it, and then sure, it returns something. But it's done something evil inside. Right? We can see that that's true just by executing it a bunch of times. We're like, yeah, I mean, technically it returns the same number every time, but it changes this state. It changes this global variable. That's bad. That's not okay. So now here's a question for you. What about this third function, impure function 3? Sorry, that's not my example just yet. Impure function 3, I can quickly show you. That's also sketchy because call it. Sure, it gives me something, but then if I call it with a different global state, executions I said, right? If I call it with a different global state, it suddenly gives us a different answer. So that's bad. We don't want that. I was going to say something. What was I going to say? Who knows? Can't have been that important. Okay, so global state, bad. Don't mess with it. Don't access it. Okay, fine. I'll be getting to my... Sorry, on one laptop screen, I have like my copy-paste pad really tiny to the side, so I can't see what's coming up. This is very exciting. Okay, here we go. Final examples. Thank God, right? Back to some fun JAX stuff in a second. Here's another classic. This impure function does a lot of bad things that are somewhat, if you've ever used like Haskell or some other functional language, like all this stuff, and these things are a little tricky at first. Like, printing something out. It changes the global state. Right? What I see in my console window or whatever is part of the global state. So this is already changing things. Asking for the user input, that's definitely impure. Like I could put in something different every time, and the results of this function might change. That's no good. The function must only take in information that it was explicitly given in its arguments. And finally, this one here, where I asked for the current system time, that's obviously also a bad idea, right? Because that's going to change from execution to execution. We're again accessing something we're not allowed to access. So now one last function, impure function 5. Which constraint does this violate? What's wrong with it? It's impure. I've given that much away. But what is it actually doing? And that's kind of yeah. Let's see. I'm gonna wait a few seconds to see if someone wants to dare guess in the chat. I also don't know if I see the chat. It won't go down. Yes. Okay. Yeah. That's the. That's right. Wow. First try. Damn. I like when people struggle, I like when they get things wrong. It's much more fun. But yes, so it accesses global state, accessing the seed and the state of the RNG, and it also mutates the state of the random number generator, right? It advances to the next state so it can get a new fresh random number. So it kind of violates both these things of taking in things it wasn't supposed to look at, and taking and having effects that it wasn't supposed to have. Like the nature enthusiasts among us might be familiar with the take nothing but memories, leave nothing but footprints. And that's kind of applicable here. In fact, one mnemonic that I found super useful for understanding purity and for having like a very quick and easy test is this one. If the function you're implementing could easily be a lookup table, or it could easily be cached, then it's pure. Yeah. This is obviously not true for this one, right? If I give it like a nice cache decorator, wow, now my function is cached and all the randomness is gone. So that's not true. Same for these things, right? I can't just cache user input or cache the printing because it has to happen again when I call this function. On the other hand, where do we have a nice pure function? Over here. This function, I could totally cache that, right? It's never going to change. Doesn't really depend on anything else. So that's a really nice and easy way to tell whether your function is pure. If you can convert it to a lookup table or you can cache it, it's pure. Okay. So how are we going to do this? Is it time to jump back to the slides yet? Who knows? We'll find out. How are we going to build a loss function that is pure? If we do it like this, we are still using this weird object-oriented skeleton that we had up here, right? Where it owned its own weights and it used them in its method. But just like our pure example where we passed the list and then created our own list and only mutated things inside, this will be a pure loss function, right? Yes, it creates this stateful class, and then it mutates the stateful class, and then it calls the stateful class that accesses its own things statefully. But in the bigger scheme of things, if I just look at this function, well, it just takes W and a V and X's, Y's, and puts them in there, and then calls this result, and then the linear regressor is destroyed afterwards. No trash is left. We don't look at anything we're not supposed to look at. So this loss function would be pure. And again, gives us the result that we wanted. You can use this loss function, in fact, to already start training this thing. Again, let's expand our data a little to make it less underdefined. Here's a loss function. We pass the stuff in. It's very beautifully pure. And we take the gradients with respect to the first two parameters. That's what this is for, because usually grad only gives you the gradient for the first parameter, but we want gradients for W and for B. So we tell it, give us gradients for both of these things, and that's what's coming out. DW, DB. Okay. And now we have this class myRegressor that we kind of keep around statefully. That's okay. We're not letting JAX know. JAX doesn't deal with this. This is like our own record keeping. And we can mutate it. again, doing this very simple SGD, and then predict with it. And we see again, trains beautifully, gets close to 7. That's all we want. That's all we were asking for. Okay. Now, if you give me a second, I'm sneakily looking at my phone to see when I'm jumping back to the... Okay, no, not for a while. Neat. You get to see more notebooking. Love it. Okay. So this is nice and all, but it's kind of silly to have this my regressor class and not use its function and just use it to hold the W and the B for our own bookkeeping, right? That's what we're doing here. Like, we might as well not bother, you know? Screw this. Get rid of this, and let's store our parameters in a nice dictionary. You know, there's not really much of a difference, except the dictionary feels lighter and better and more modern and sleek. Love that. So with this, we might change our method slightly to now have our pure loss function not get W and B, or in other words, not enumerate parameter by parameter by parameter, but only have this one dictionary params, and then still use it as before, get the W entry, get the B entry, calculate the loss function, easy peasy. Loss function is a little different now because we still have x's and y's to the big data set. That's fine. Cool. So we've saved ourselves a bit of typing right up here. That's nice. I'd love to save myself some typing. But it gets even better. Because now if you're asking yourself, okay, well, this is a pure function, but this is not a number. What the hell is a gradient for a dictionary? So what do you think? If I do this, if I call jax.grad on the loss function, now again, we're only interested in the first parameters because we've nicely consolidated it. That gives me the gradient function. And I evaluate it on my current parameters and my data set. What's the type of gradients going to be? Again, we'll open up the chat. Give you a second. Yes, exactly. It's a dictionary as well. It's a dictionary that uses the same keys that we've been giving, W and B, and the values are now the gradients calculated by JAX. And these are the same gradients we had before, and we're going to see them a bunch more throughout this notebook, so get familiar with these numbers. But yeah, it just works like that. This is amazing, right? Like in my loss function, I don't have to enumerate all the parameters. In here, I don't have to enumerate all the parameters. In here, I don't have to enumerate all the parameters. The only place I ever really deal with the parameters is when I use them in my loss function. That's pretty cool. And pretty convenient at that. So now with this, we can again do this thing where we update our current parameters, go through all these things. And if you're looking at this, you might already be like, why don't you just loop through all the keys and not write things out line by line? And patience, we will get there in just a second. What matters is loss goes down, 7.5 goes to 6.1. Amazing. We've done it. The machine has learned. So I said we're going to get there in a second, and the second has come. If we get our gradients like this, and we know they're a dictionary now, right? We could define such a function called like an update combiner. This is really, if you think about it, like a very bare bones optimizer skeleton, which would take a single parameter, a single gradient. Like these could still be tensors. They don't have to be scalars, but a single item. Give it a learning rate. Let's be fancy so we really see what's happening. And it just returns the new value of the parameter, which is parameter minus that gradient, just as before. And now what we can do is we can map this update combiner over the tree. In this case, it's just a dictionary, but we're going to see in a second why it could be called a tree. By passing it to this function called jax.treemap, together with the params and the gradients. And it is going to do this work for us of going through all the keys in this dictionary or all the leaves in this tree, updating them and giving us a new object. What is the type of my params? Kind of obvious at this point, or at least we would hope that it would be something that we like. It is a dictionary that contains the new parameter estimates, and indeed, these new parameter estimates that come out of the update, again, have made our loss go down. Wow, this is great. To update a question in chat that I just saw, PyTrees I'm going to mention in a second. What does weak type mean? I wondered about the same thing. When I checked out this notebook this morning, I was like, all right, what's changed in JAX since last time? This wasn't here. That's got to do with the type promotion semantics. So when I put in something like, where do we have it? Yeah, over here. I say W is 0.0. What is that type? Something floating point, right? But is it like 16, 32, 64-bit? Maybe it's even a complex number. Just by writing 0.0, that's not really specified. And we could say like, oh, this is actually an array with b-type something, right? Oops, can't type. And so on. But if we're not going to do that, then JAX is like, I don't really know about this one. Let's say this is a weak type for now. That's the gist of it. Maybe someone with more experience working with this can weigh in the chat too. But yeah, I wanted the very same thing. Is there something else? I don't think so, right? Cool. So let's move on with that. We've made the loss go down. We've used jax.treemap, which used to be called jax.treemultimap. You'll still see that in the old blog post and stuff, but it's a small change. You really just use it the same way. So that's wonderful. Now that we've done some individual loss steps, let's let the machine do this for us. We do a few steps of SGD. Again, this is all the same stuff we've seen. We take the gradient of the loss function. This we don't actually have to use every loop. We could just have done it once and then cache the function, but who cares? Go slow. The world is beautiful or something. And then do the tree map update. And this is a little awkward that we still have this predict method coupled to our linear regressor. And now we have to manually transfer the weights from the dictionary into this object that holds our magic methods. But we're going to get there in a second. What matters is thing trains. Great. That's all we need. So with this all done, it is time for an aside. So if you want to catch a break, this is it. This is going to be a fun little thing that might help you understand PyTrees a little better. And someone already mentioned this in the YouTube comments, and I think it's one of the most amazing and beautiful things in JAX. You are wondering maybe, why can't we do this thing with dictionaries? How does JAX know that it has to go through dictionaries? Like somewhere in JAX, it says numbers are numbers, tensors are numbers, dictionaries are close enough to numbers. They'll have like numbers in them. That's good enough. And the whole API is talking about PyTrees as things that have numbers in them that we can take out and do math with. So you might really think of it as a tree. This makes most sense when you think of like maybe a nested dictionary, right? A dictionary that contains some dictionaries that contains some dictionaries that contains some tensors. And so JAX is somehow able to maintain the structure, do things on the tensors in between, like take gradients, and then recreate this tree with that structure with the new numbers inside. And the beautiful thing is we can do that too. It kind of lets us do this, where we can register new types of PyTree nodes. Numbers, tensors, lists, dictionaries, and our class linear regressor. We're going to make that a PyTree too. The way you do that is you call JAX tree util register PyTree node, give it the class that you want to register, and then you give it two functions. These functions are pure because all beautiful things are pure, are flatten and unflatten. The flatten one basically takes this complex object, this PyTree node that we have, and converts it into a representation that sort of teases apart the two parts of this structure, whatever the structure may be. One part, we call the leaves, is really a tuple or a list of all the tensors in there, the stuff with the numbers, the stuff that JAX is going to be dealing with. And the other part concerns the greater structure. Like if there's some structural information that is not numerical, that we can't differentiate through or anything like that, but that is important in this object and must be kept for operations like tree map. In this case, since we only really have these two scalars here, I mean, we just make leaves the tuple and there's no auxiliary information really. and we return that tuple. That's what you do for flatten. And then for unflatten, you basically do the same thing in reverse. You go from leaves and auxiliary information back to the object. However, unfortunately, due to historical baggage, the argument order is reversed right here. So be careful with that. Again, since we don't really use aux, I've just underscored it. We use the leaves. We say it's a tuple W and P. We know this because we've created it ourselves. And then we create a new linear regressor, assign the right values, and return it. And so with these functions, JAX can now, when it is asked to differentiate through a linear regressor, it can be like, all right, I don't know what the fuck that is, but let me call flatten on this thing, and then I get a tuple with like numbery things that I do know what to do with, and auxiliary things that I'm just not gonna touch. All right, you do your thing on the numbers. Now you call unflatten, put it all together, and voila, you have a new linear regressor. This is quite beautiful magic, in my opinion. I greatly enjoy registering PyTree nodes all the time. And with this, we can now do cool things. Our last function can now take the regressor as an object and do the RMSE. And okay, that's fine. We were able to do that before. What we weren't able to do before is get gradients. So if I now call JAX.grad_loss function, well, we get a function that gives us the gradient with respect to the first parameter, which is my regressor, my class. So what's the type of gradients? What do you think? Yeah, it leaves the PyTree structure basically untouched in the aux thing. All that matters is that leaves is a tuple or a list. I don't know if that matters, but I'll just make it a tuple. Actually, anyway, a tuple or a list, and that's all you need to do. A tree, yes, it's a PyTree, but what kind of PyTree is it? Yeah, that's right. It's a linear regressor. Right here. JAX has created this class for us using its magic and really using our hard work of writing the flatten and unflatten methods. That's pretty cool, I think. If you don't think so, that's fine. You can stay. And we can look at these properties of this object, these members of our class, and yes, we get these familiar gradients. All has worked out at before. We can even do tree map with this thing because tree map, again, works with PyTrees. So we just combine the original regressor with the gradients regressor, and we get a new regressor. And under that new regressor, the loss has gone down. So that's pretty much my aside. If you thought this was cool and you want to see how far to take this, you probably want to find a way to automatically write flatten and unflatten logic for people's new classes, so they don't have to do this. Maybe you use type annotations. Maybe you hijack the methods, kind of like PyTorch. Whoops. And you want to do something with initializers and randomness. And if you follow this through, you might get this little framework that Sasha, Rash, and I sketched in 2020, where we were basically following this idea and seeing how far we could get. It's not really like been a thing at all. It's really just a fun project, and we kind of stalled on making batch norm work because statefulness. But if you want to take a look at it, it's there. It could be fun. All right. So now let me think. Where do I switch back? Okay, cool. I think it's time to switch back to the slides. Less typing, less room for mistakes. Love to see it. Apple PyTree, I love that. Cool. So what we're going to be doing next is forget about all this PyTree stuff. That's what I'm saying. It was an aside. It was fun. We had a good time. We had laughs. But, you still wake up the next morning, sober up. And now it's time to get back to work and actually think about what we can do to make this dictionary-based writing or whatever we're doing just a little bit nicer. What we want to do is make the user's life easy. The user's gotten very used to writing these stateful methods like in PyTorch. And say, yeah, fine, write your stateful methods. I'll clean up your mess after. How do we clean up the mess? Here's what we're going to be doing. And this is really the key idea behind these frameworks and behind this talk. we're going to have this class regressor as before. It owns its weights. And if this was PyTorch, then this function f that takes in an x, yeah, it would use the weights, thereby access state outside of the function, which would not be pure, and return its y. Wonderful. What we want to be doing is let the user write a class like that, but actually do a little trick. What we want to be doing is called a purifying regressor, and I totally made this up, but I thought it sounded pretty cool. Where we don't really start out with a weight. That's kind of weird. There's none here. Well, we'll deal with that later. And the user writes this function f just as before, saying, oh, I access my weight, blah, 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 things will be fine. And then we are somehow tasked with the job of creating a purified version of that f that now actually takes in the parameters alongside the data. First thing it does is assign self.w to this information it just took in. And so now what happens when we next call this dirty function f is, yeah, we pass in the x, we get out a y, but when this function f accesses self.w, it doesn't actually access anything from outside the function, because we've just defined self.w to be the argument itself. So the information flow doesn't leave the function. We don't actually violate purity, because we've sort of tricked this function. It's running in a kind of sandbox, if you will. So after that, I mean, we might not bother, but I like to leave things clean. We just set self.w back to none, and we return the y that came out of the dirty function. And as you can see, all the arrows are inside the function. Nobody writes anything anywhere they're not allowed to, and nobody reads anything from where we're not allowed to. So that's pretty cool. And this is kind of how I want it to be. I want to have this sort of fancy magic artisanal base module class, the same way we have in all our favorite frameworks. That's going to have to do this work for us, this purification somehow. I don't see it in my code. That's annoying. And I want to define my impure function. Like in this case, we have an impure RMSE that takes in the data. So far, so good. And then uses its parameters. Now, this is not quite self.w, which maybe you could make it work, but it'll be much easier to compromise on saying, fine, we have like a method called getParam that sort of acts like self.w, right? We're also going to pass this method an initializer. That looks kind of weird, like we're mixing things that weren't supposed to be mixed, but we're going to see why that's going to be real useful later on. And so now these w and b that we get from getParam, we are legally allowed to assume are actually just normal tensors. Nothing weird about them. So we use them in our math and return our value. Now something's got to happen here. There's got to be some magic that's going to come from the fancy magic artisanal base module class. And maybe it's called purify or something. We'll see. We'll figure it out, We want to have a function that basically purifies this impure function into a purified function. And I'm already going to spoil, we're going to get an initializer out of this. That's why we mixed it up in there. So we don't have to enumerate like, okay, here's our dictionary, w is 0, b is 0. Let's just like this function, take care of it, Why work when the framework can work for you? And then once we get my params, that's just going to be a dictionary, just as before. So you see that getParam is actually accessing this dictionary, spoilers. And so we can call a purified thing with it. We can do gradients of the purified thing and call that with it. We can do JAX tree map and get our new parameters, just as we've seen before. Okay. So let's implement this thing first. Off to the notebook, it says. And that's what we will do. Here is my draft of what I want this to look like. We have the purifying regressor. It uses self.params as opposed to self.getParam because, let's build this up simple. Let's not do the initializer bit just yet. Keep it simple. Okay, this is great. This is like what I want to write because I'm boring and I never want to learn new things and I want to write PyTorch code. And supposedly that's a good thing to do. We have params initially set to none. And then this purified version of the function sets self.params to the params that were passed, calls the impure function that tries to use self.params, but joke's on you, there's nothing actually you're getting that isn't coming into this function to begin with. and then we zero it out in the end just to be clean and return the result. Initialize parameters by hand for now, get the value and grad, because value and grad is nice for what we want to be doing when we look at the loss and the gradients. And the purified function, you will see, is actually working, because yeah, we can get gradients through it, and they are the same gradients we've been seeing all along in this notebook. That's delightful. Let's see. How can we make this basically now do the fancy artisanal base magic framework? I would like to not write too much code. Well, this one's going to be a little bigger, so I'm going to decrease the font size. Let me know what's a good compromise. Like maybe this would work. So since we're going to be doing pure execution and initializing, I was like super, uber, hyper careful and anal about it, and just added 2 flags to this class that says, are we running in pure mode? Are we running in initialization mode? Ideally, they should not be true at the same time. There's better ways to do this, but yeah, whatever. It's good enough. Parameters are known as before. Here's our function getParam that I hinted at in the slides, and that is now going to depend on which mode we're in. If we are initializing, then we got to check, do we already have that parameter in our params dictionary? If so, nothing we need to do. If not, create it with the initializer. That's why we pass in the initializer as the 3rd argument to getParam. Okay, and then return the parameters so the function can continue. If we're running pure, well, then we basically assume that the self.params has already been hijacked, and we can just use it. So sure, return self.params, good for you, enjoy. And if we're not running in initializing or in pure mode, well, then we're impure. And we don't like being impure, so we raise an exception. Wow, so much guardrail, so much safety. Feels very German. Now we're going to have a bunch of functions. This one is basically the wrapper for the initialization logic. It gives us a function called initializeParams that is returned, that sets us to initializing mode, gives parameters an empty dictionary, calls the method that it was passed. Then when the method that may very well have been impure, and we assume it to be impure, is done, we set initializing to false, we return self.params, and we set self.params to none to not risk leaking information. The pure method works much the same way, and we've already seen this before now, where we create a new pure method given an impure method called method. We set are we pure to true, we set the parameters up, and we call the method that is impure, but joke's on you, we've already hijacked self.params, and again, zero it out after, and set the mode back to the original one. The final one is the API that we want to expose to the user. So maybe I should have underscored the other ones, but I hope you'll forgive me. Given a method, I want us to return a tuple that consists of the purified version of the method and an initializeParams version of the method that basically is going to initialize all the parameters and give us the parameter dictionary based on all the parameters that were used in this method. That's a lot of stuff. Like, this is a big cell, and if you're a little overwhelmed, I understand, but we're pretty much done at this point with the hard lifting. Now we just got to use it. This is pretty much like what I wanted to see in the slide. We have an impure RMSE. We use self.getParam. We give it an initializer. That's very simple and boring. We have an impure predict that also uses WMP and gets getParam the same way. And then we call this purify that we just defined up there, and it gives us the purified one and the initialized one. We call myParams, and let me actually add this here, because why not? We can see what's happening. And that's going to be, oops. What did I? Oh, I didn't execute the cell. That would have been useful. So we should see the initial parameters pop up in a second. That should be 0, 0. Yep, except we didn't have to write it down. The framework did it for us. And then we can get the loss before the update. We get the gradients. We get the loss after the update. It's all beautiful as it was before, except we had even less code to write. And that's kind of the beauty of it all. Again, obligatory mechanization of turning this into like a loop. Yeah, our loss goes down, our correctness goes up, you know. And that's really all I'm going to show you from this notebook. to end this talk with, let's kind of recap from what we built. We built this thing up here, right, where we have a get param, and we have this purify, and then we call initialize and purify RMSE. But when we now look up over the landscape of all these beautiful frameworks blossoming in the distance, we've kind of re-implemented exactly what they're doing. Right? This is DeepMind's Haiku, which was my framework of choice at the time. It literally has a method called getParameter, and it gives it the initializer, and then it calls our purify, it calls transform, and it gives you transform.init and transform.apply, which is our initialized params and our purified function. Exactly the same thing. A little bit more belts and whistles to deal with randomness and state and all that stuff, but we get the idea. Or more appropriate maybe now these days, where Flax has become a big thing. If you look at flax.linen, it kind of uses this annotator annotate compact to do the transformation for us. So the class already turns its call method into the init and apply pair. But apart from that, again, the same thing happens. We have this method called self.param, gets its name, that accesses the dictionary that's underneath it all. We have an initializer, and in this case, we have a shape too. And then we have init and apply, same as we did. Well, again, with randomness handling, which we skipped over, but that's really all there is to it. So that's really all I have to say about this. We've kind of started from first principles and tried to figure out how could one do this, and messed around with some ideas, and in the end we came up with something that's pretty much exactly what the frameworks are doing, because we all come up with the same ideas often enough. So if you're interested in more details about this, more complications, a little bit more background, maybe a slower explanation, just more code, this is all on my blog post, and there's a notebook version of it too, and you can see the slides of this talk and the recording from back when, and can compare how I'm doing today. You can follow me on Twitter if you want. I'm not really active on Twitter anymore these days. It's one of the addictions that I've actually managed to replace. So yeah, let me know if you have any questions, and I'll be here.
Yeah, there is one question, because you answered them throughout this stream. So if we separate the params dictionary from the architecture, how do we know when the parameters are broken by a change in architecture?
So you would kind of wonder, like, how do I tell whether a dictionary is compatible with the architecture that it's using, right? I mean, I really think that there's no good answer to that. Like, you could do something like, okay, let's take the architecture and like hash it and store the hash in the dictionary. That'll be a quick test. Maybe that's what some frameworks actually do. I don't actually know. I feel like I vaguely remember something like that, but I'm not sure. But even if not, I mean, this is one of those things that will break. It'll just break. If you access a parameter that isn't there, it breaks. And I am of the opinion that things breaking is a good thing. I'd rather things break than be wrong. But that's kind of what I would say this is all about. It gets a little weirder when you have like parameters that are in there but aren't used, but then the optimizer uses them, so then things get wacky. But yeah, I guess, like hashing the architecture somehow is probably the best way to go. And again, I don't know what exactly frameworks are doing.
And Alex is asking, with the gradient being another linear regressor, is calculating the second derivative as simply as just calling loss function on the regressor again?
I don't see why not. So where did we first define this? This is all torch. Never mind.
You should go a little below, I think.
Side. Okay,
Around, yeah.
Oh yeah, here we go. Cool. And this is what we have. So let's add another cell. And let's just call it JAX or grad twice. It's the worst that can happen, right? And this is a function. I'm going to call it separately with my regressor x's and y's. Can it happen? Well, we'll find out. Gradients are defined for scalar output functions. Ah, right. So what we need is okay. So it's not really a gradient in this point, right? It would be like a Jacobian or something. Wait, no, not Jacobian. Hessian. Second is Hessian. Something like that. Yeah. I wonder. No, I don't actually know. No idea. Maybe it's something obvious and easy, and I just don't see it right now. But that's a fun one.
I don't think we have any more questions. Thanks a lot for this presentation. I loved it. I will definitely check out the follow-up one. Alex is saying you need to pass the returned gradients into same function returned by JAX grad loss function. How is that different though? I don't know how
that
it
should
is
be
different.
that should be the same thing. Like, because loss function gives you a scalar. JAX.grad gives you executing JAX.grad gives you the linear regressor. So the type is messed up anyway. I mean, yeah, you can't get a gradient with respect to a regressor. You could do it with respect to all the individual leaf node entries or something. But I think really in this case, since we are dealing with like more than scalars, we are dealing with like multiple dimensions. The second gradients would not be gradients. They would and should be something quadratic.
So Christian saying grad loss function.
What would that mean?
Why would you run it over
like that? That would be
that
would be something, but it would not be the second derivative. Yeah.
Yeah, this is different than the second derivative, I think. But I'm not a JAX pro, so and he is a good one. It's acting on the function without arguments, so that doesn't work. Okay, Christian is saying, not saying this is right, and he says, but it will give something.
It will give something, that's for sure. Yeah, I think the types will work out on that one. That's true. That looks like it could work out. Yeah.
Anyway, there is a Hessian function, by the way, he says.
That makes sense. I mean, I don't know how it works in this case because we have multiple parameters that are not in the same tensor. So you get some weird cross tensors. Like the object wouldn't really match, right? Because you have these interactions between W and B and they're stored in different tensors. So you need like some WB and BW tensors. So I think it will get a little messy, but I might be completely wrong on that. Who knows?
So thanks a lot for coming today. I really enjoyed your talk. And thanks a lot. I'm going to take you off now. See ya. We are going to have another round of talks on 17th, and that will be the day 3 of our talks. And we have speakers from Google Brain. We will have Boris, who created the DALI Mini in the previous JAX sprints. And stay tuned and also set your reminders for the day 3 of them. Thank you so much for chiming in, and I will see you around.